Hey everyone, welcome to week 3 of General Chemistry. I am your Ma'am Ariantine, your lecturer for this week's lesson. So the general objectives for this week are: you are going to learn how to calculate the percent composition of a compound from its formula, and you are going to learn how to calculate the empirical and molecular formula from the percent composition of a compound. So our topic for this week will be all about percent composition and chemical formulas. So before we begin with percent composition, let us try first to understand what does the law of definite proportions state. So the law of definite proportions state that any sample of a given compound always consists of the same elements in the same proportion by mass. So let me highlight this one. It says that in definite proportions, a compound will always consist of the same elements in the same proportion by mass. So to understand this one, let's take water as an example. So as we all know, water has a chemical formula of H2O. So in order for us to call a compound as a water molecule, it must have 2 atoms of hydrogen and 1 atom of oxygen. So that is the definite proportion of a water molecule. It's 2:1. Now what if we are going to change this one, for example, into H3O5? Can you still call this H3O5 as water molecule? The answer is no. So if the ratio of the elements is different from the specific ratio, then it is not the same compound and therefore will have a different name. So the law of definite proportion is telling you that for a given molecule or for a given compound, it will always have a fixed proportion for that molecule. Okay? So the main idea, therefore, of percent composition grounded from the law of definite proportions is that a compound contains a constant proportion of its constituent elements. So in percent composition, we are therefore calculating the percentages of each constituent elements that make up a specific compound. So in water's case, the percent composition, therefore, we are calculating how many percent of hydrogen is present or how many percent of oxygen is present. So to better understand, or mathematically speaking, therefore, we compute percent composition of an element by this formula. So percent of the element, A represents the element, is equal to the atomic mass of the element times the number of atoms of that element in the compound divided by the formula or molecular mass of the compound times 100. So in simple manner, it's just dividing the mass of part divided by the mass of the whole times 100. So how are we going to compute the mass of the part and the mass of the whole? Let's take this example. Sodium carbonate, which has a chemical formula of Na2CO3, is commonly used as an additive in the manufacture of glass or as neutralizer for chlorine in pools. What are the percentages of each element in the compound? So the first step in here is to compute for the formula or the molecular mass of the compound. So if you are going to take a look at the chemical formula of sodium carbonate, it has 3 constituent elements. We have sodium, we have carbon, and we have oxygen. So we need these elements in order to get the whole mass or the molecular mass of this compound. So we list first the elements. We have sodium, carbon, and oxygen. Now, in order to compute for the molecular mass, we need to compute first each element's molar masses. For sodium, in order to get the molar mass of each element, you just have to simply multiply the atomic mass, which is found in your periodic table, atomic mass of the element, times the number of atoms present in the compound. So for sodium, the atomic mass of sodium, as you can see in your periodic table, is 22.98. Now take note, in percent composition, we are going to use the atomic masses of the element. We are going to round the value of the atomic masses to its nearest whole number. So we are going to use whole numbers in computing for percent composition. So if that is 22.98, therefore, that will be 23 times 2. Why 2? Because there are 2 atoms of sodium based from its chemical formula. For carbon, the atomic mass is 12.01. So we are going to use whole numbers, so that will be equal to 12 times 1 because there is only 1 carbon atom in the chemical formula. And lastly, oxygen has an atomic mass of 15.99, so that will be 16 times 3 because it has 3 atoms of oxygen. So 23 times 2, that will be 46. 12 times 1, that will be 12. And 16 times 3, that will be equal to 48. Then you add these 3. So 46 plus 12 plus 48 will give you 106 atomic mass units. Okay, so this 106 is now our formula or molecular mass. Now the next step is now to use the general formula. So again, percent of that element is equal to mass of the part divided by the mass of the whole. So to explain this one, the mass of part is pertaining to the molar masses of each element. And the mass of whole is the molecular mass itself, this one, this 106. So we are now going to compute percent composition of each constituent elements. Let's start with sodium. So for sodium, the mass of the part is this 46 AMU. So we write 46 divided by the mass of the whole, which is 106 times 100. You bring out your calculator and try solving this one. So 46 divided by 106 times 100, that will give you 43.40%. Next one is carbon. That is 12 divided by 106 times 100 equals, that will be 11.32%. And lastly, for oxygen, mass of the part, that is 48 divided by the mass of the whole, which is 106 times 100. That is equal to 45.28%. Now, this means to say that the percent composition of sodium carbonate is, it has 43.40% of sodium, 11.32% of carbon, and 45.28% of oxygen. Now, to check whether your answers are all correct, the sum of these three must be equal to 100%. So, if you are going to add 43.40, 11.32, and 45.28, it must be equal to 100%. That means to say, if it's equal to 100, then your answers are all correct. Now, take note, if it happens that the total that you will get here is not exactly 100, say it's 99.90 plus something, or 100.010 plus, then that is still correct. Because if you can see in our solution, we rounded the atomic mass units to their nearest whole number. Another example. What is the percent composition of C5H8NO4, a compound used to flavor foods and tenderize meats? Write your complete solution below. So again, the first step to get is to get the molecular mass of the compound. So we have 4 elements in here. We have carbon, hydrogen, nitrogen, and oxygen. Okay, carbon has an atomic mass of 12 times 5 because it has 5 atoms of carbon. Hydrogen's atomic mass is 1 times 8 because it has 8 hydrogen atoms. And for nitrogen, nitrogen's atomic mass is 14 times 1 because it has only 1 nitrogen atom. And oxygen is 16 times 4 because it has 4 atoms of oxygen. Now, so 12 times 5, therefore, that is 60. 1 times 8, that is 8. 14 times 1, that is 14. And 16 times 4, that is equal to 64. And then add 60 plus 8 plus 14 plus 64 is equal to 146 atomic mass units. Again, this is your molecular mass, or MM. Now, the next step is to compute the percent composition of each constituent elements, starting with carbon. So, for carbon, it's mass of the part divided by mass of the whole, right? So, it's 60 divided by the mass of the whole, which is 146, times 100. So the answer is 41.10%. For hydrogen, mass of part is 8 divided by mass of the whole, 146 times 100. The answer is 5.48%. For nitrogen, it is 14 divided by 146 times 100. The answer is 9.59%. And lastly, for oxygen, that is 64 divided by 146 times 100 equals 43.84. Again, to check your answer, this 4 must be equal to 100. So 41.10 plus 5.48 plus 9.59 plus 43.84 will give you 100.01. Okay, like what I have said, if your answer is 100.0 something or 99.90 something, then that is still correct. Therefore, for this problem, this compound has 41.10% carbon, 5.48% hydrogen, 9.59% nitrogen, and 43.84% oxygen. Okay, now what if we are going to reverse the situation? What if we are going to solve this time the chemical formula from the given percent composition? So our next topic will be about how to get the chemical formula if the percent composition is already given. So, can chemical formula be derived from percent composition? The answer is yes. This usually applies during a chemical analysis when a compound is broken down into its elements to determine its percent composition. So to further understand, let's take this example. So what are the empirical and molecular formula of a compound that is 40.27% potassium, 26.78 chromium, and 32.95% oxygen? The molar mass of the compound is 194.2 grams per mole. Now notice from the given problem, the value or the unit of the elements is expressed in percentages. So they are all in percent. And the unknown is empirical and molecular formula. So what are we going to do to make this percent into grams, because that is what we are going to use? Now, the best way to solve this kind of problem is to assume that 100 grams of the compound is composed of the elements with masses corresponding to their percentages, so that we could remove the percent sign. The best way is to assume 100 grams of the sample. Okay, so the step 1 therefore is to determine the given. Since we assume 100 grams of the sample, this 40.27% potassium therefore is also equal to 40.27 grams potassium. This will become 26.78 grams chromium and 32.95 grams of oxygen. Those are the given. Plus the 194.2 grams per mole molar mass. So if you already determined the given, the next step is to convert the mass to moles. So how are we going to convert mass to moles? Here is the formula. The mass of the element is multiplied by 1 over the atomic mass of that element. So we are going to convert each element one by one. So let's start first with potassium. So it's from the formula, you just have to get the mass of the element from the given times 1 over the atomic mass from the periodic table. So for potassium, the mass of the element is 40.27 grams, that's from the given, times 1 mole divided by 39. That's the atomic mass. So that will give you 40.27 grams times 1 over 39. That would be equal to 1.03. 1.03 moles. The next one is for chromium. The mass of the element is 26.28 grams times 1 mole divided by the atomic mass of the chromium, which is 52. So cancel the grams. cancel. So that mole will be the unit. So 26.78 grams times 1 mole divided by 52, that is equal to 0.52. And the last one is oxygen. So the mass of the element is 32.95 times 1 mole divided by the atomic mass, which is 16. So that will be equal to 2.06 moles. Okay, so we are done converting the mass of the element to moles. So the next step now is to write the chemical formula using the mole of each element as its subscript. So if we are going to use these values of mole in writing the chemical formula, the outcome will be for potassium, that is 1.03, for chromium, that is 0.52, and oxygen is 2.06. Now if you can notice, the subscripts are expressed in decimal number. And we all know that chemical formulas are not expressed in decimal numbers. It must be in whole numbers. So the question is, how are we going to make these decimal numbers into whole numbers? That will be the next step. So step 4, therefore, is to reduce the formula to the simplest ratio by dividing the smallest value of subscript to each subscript. So we are going to divide the smallest of the subscripts to each subscript. So going back, potassium's subscript is 1.03, chromium is 0.52, and oxygen is 2.06. So the smallest subscript is 0.52. Therefore, we are going to divide each by 0.52 since this is the smallest value. So that will give you now 1 divided by 0.52 is 1.98. Now take note, if the value in here is near to its whole number, then we immediately round it off. So this 1.98 is approximately 2. For chromium, that is 0.52 divided by 0.52, of course that is 1. And for oxygen, that is 2.06 divided by 0.52, that will give you 3.96. Again, it's near to its whole, so 3.96 approximately, that is 4. Now, we can now therefore write this chemical formula using their whole number subscripts. So that will become K2 CR1, 1 is not written, O4. And from this point on our step 4, this is now your what we call empirical formula. So from this step, by dividing each subscript to the smallest subscript, we could get the empirical formula. Now the next step is to compute empirical mass from the empirical formula because we still need to find the molecular formula of the compound. So, when computing for empirical mass, it's just like computing for the molecular mass that we did in our present composition. So, using this formula, K2CrO4, the potassium, chromium, and oxygen, potassium's atomic mass is 39 times 2 because we have 2 atoms of potassium. And then for chromium, we have 52 as its atomic mass times 1 because we only have 1 chromium in here. And for oxygen, we have 16 times 4 because we have 4 atoms of oxygen. So that will be 39 times 2, that's 78. 52 times 1, that's 52. And 16 times 4, that is 64. And then you add this 3. That is 194 atomic mass units. This is now our empirical mass. Next, what is the use of this empirical mass? Now we are now going to divide the given molar mass by the empirical mass. Why? On this sixth step, we are looking for a multiplier or a ratio for us to use to multiply to the empirical formula to get the molecular formula. So in step 6, we are computing for a ratio or a multiplier. So here is the formula. You just have to simply divide molar mass by the empirical mass. So the molar mass is already given in the problem. That is 194.2 grams per mole. And the empirical mass is the one we just computed. That is 194. So 194.2 divided by 194, that is 1.001, 1.001, or approximately 1. Take note, in looking or in computing for a ratio or a multiplier, it must always be a whole number. So we round this into 1. Since we already have the empirical formula and we have a ratio number or a multiplier, we now multiply the ratio or the multiplier to each of the subscripts of the empirical formula to get the molecular formula. So going back, the empirical formula is K2CrO4 multiplied by our multiplier, which is 1. So K2 times 1, which is the ratio, Cr is only 1 times 1, and then oxygen is 4 times 1. So the final answer is K2CrO4. This is now our molecular formula. And this compound, K2CrO4, is also known as our potassium chromate. Now, the question is, what therefore is the difference of empirical and molecular formula? So, empirical formula expresses the smallest whole number ratio of the atoms present. When we say molecular formula, it states the actual number of each kind of atom found in one molecule of the compound. So how is that? Let's take a look at this table. For example, this acetylene. The molecular formula for acetylene is C2H2. So if we are going to make or to find the empirical formula of acetylene, we just have to simplify the molecular formula because molecular formula shows the actual number of each atom, while the empirical formula is just a simplest formula, or it's a simple formula from the molecular formula. So you just have to get the greatest common factor of the subscript. So in this case, C2H2, your greatest common factor is 2. So you divide each subscript by 2 to make it CH only. So again, empirical formula is a simplified formula of molecular formula. You may also take a look at the other examples. Another problem for empirical formula. The chemical analysis of aspirin indicates that the molecule is 60% carbon, 4.44% hydrogen, and 35.56% oxygen. Determine the empirical formula of aspirin. So in this problem, we are only looking for the empirical formula. So again, the first step to assume that 100% or 100 grams of the compound is composed of the elements with masses corresponding to their percentages. So we determine the given. So 60% carbon, that means to say we have 60 grams carbon, 4.44 grams hydrogen, and 35.56 grams of oxygen. The next step is to convert these masses to moles. So for carbon, we have 60 grams of the element times 1 mole divided by the atomic mass of carbon, which is 12. So 60 times 1 divided by 12, that is equal to 5 moles. 5 moles. Cancel grams. Next is moles of hydrogen. It has 4.44 grams of hydrogen times 1 mole divided by the atomic mass of hydrogen, which is 1. So 4.44 times 1 divided by 1 is 4.44. And lastly, for oxygen, we have 35.56 grams times 1 mole divided by the atomic mass of oxygen, which is 16. So that is equal to 2.22 moles. Don't forget to cancel grams. The remaining unit is moles. Okay, now we already converted mass to moles. The next step is to write the chemical formula using the mole of each element as its subscript. So it will become C5H4.44O2.22. Again, we need to simplify, or we need to convert these decimal numbers into whole number ratios because chemical formulas only use whole numbers. So for step 4, we are going to reduce the formula to the simplest ratio in order to get empirical formula. So the smallest value of the subscript is 2.22. So that will be the subscript, therefore, will be all divided by 2.22. So that will become 5.4 carbon, 5 divided by 2.22 will give 2.25. For hydrogen, 4.44 divided by 2.22, that is exactly 2. And for oxygen, 2.22 divided by 2.22, of course, that is 1. Now notice on this example that at this point, the subscripts are still in decimal number. Now we need to remove this 0.25, or we need to convert this 0.25 into a whole number. So what are we going to do? We must look for some multipliers that could convert the decimals to whole numbers. So if that is 0.25, we should multiply it to 4 to make it a whole number. So we are going to multiply this whole formula by 4. Okay, so that the result will become C 2.25 times 4 will become C9. And then H2 times 4 will become H8. And then for oxygen, 1 times 4 is 4. Now notice that they are already in whole numbers. So the final answer is C9H8O4. That is the empirical formula for aspirin. Okay, thank you for watching this lesson. I hope you learned something for this week. If you have any questions about our lesson, feel free to post it on the discussion board in your LMS, and you may also post your answers from the practice problems found in the learning content of our lesson for this week.